Hello everybody. Today we are going to implement a small and tiny blockchain. This blockchain will be implemented by Python, and we are going to understand the techniques behind the blockchain. First of all, we have to define a new file and write whatever, like pass, anything is okay, and then save the file by we call it Osama coin.python. Then write the code inside the Python. First, we have to define a block. We have a blockchain, so we define the block class. Block. Okay, and the class has an constructor defined as init. This is the constructor of the block class, and we pass the current object and the value called nonce. We will talk about this nonce in the subsequent videos, and stamp and transaction value and previous hash, because we don't have a previous hash, we make the default like that, empty string. So this is the constructor of the block class. So we define new variables for the class inside the class itself, and the constructor takes all of these values and pass it to internal attributes of the class. So nonce and then stamp equal stamp, and then self dot transaction equal transaction, and then self dot previous hash equal previous hash. Okay, now we have another properties called hash, the current hash of the block. We defined the previous hash, but we didn't define the current hash of the block. To define the current hash of the block, we have to define a function to calculate this. We want to define a function here, so we define another function called calculatehash, and it takes nothing, and it contains the calculation of the hash function. So we need a library that contains SHA-256. SHA-256 is a hash function, and Python has not defined to use SHA-256, so we have to tell him how to use it. So we have to install this library from here. To install it from the command, we use the command python -m pip install -u cryptography, and it's going to install it right now. But I think we have already up to date. It's already installed, so no need to install it again. But anyway, if you want to install it in your machine, you can use the exact command like that. So it is already installed, so I can use it. So to use it, we calculate the hash function of the data that this data, the blocks data, like nonce, tstamp, and transaction, and previous hash. All of these together, we are going to calculate the hash for the block. So we define a block string, and this the block string is, we need libraries called JSON. Here we have to import the libraries. We import hash library. We also import JSON library. We needed to define some data. JSON library has a method called dumps, and it takes a dictionary. By the way, the dictionary, you have to pass a dictionary to it, so we have to write the dictionary one by one. It takes some time, but anyway, you don't have another option. And for nonce, and this for tstamp, also to define tstamp, and you say self.tstamp, and for the transaction, you define the transaction, self.transaction, and for the previous hash, you define a previous priv hash, self.priv hash. And the second parameter we pass it to dump is called sort keys equal true. Sort keys equal true, and we need to encode the entire string, so we'll be able to translate it into string after that, and pass it to the hash function. So we return a string. We return string hash library to this .cha 256, and this is the exact function that makes the hash. This is the method that makes the hash function, is called the hash function, and we pass the block string to it and change the block string to hex digest to be able to see it. And that's for it. Now we can find something useful. We can test if our function is working, our class is working or not. But now we need to define how to print. We can print the hash value here. We can define another function called print hashes, and we print the hash, previous hash, self dot previous hash, previous. We have to define self over here, forget it, and then self dot previous hash, and we print also the current hash, so we will see all of them together. So we print the self.hash value, but we didn't call the calculate function, so we have to calculate our hash over here. So we call the self.calculate hash here, .cal hash, so we're able to see a result of the calc hash. Now it is time to test our class. We define a new object of the block class. We call it bBlock equal block of it has a constructor, so we have to make to pass the parameters to pass the data to it. For example, if we call it number 1 and we put a t-stamp like for example 01 02 2018, and then we pass the value of the transaction, which is $100, and the previous hash, because this is going to be the only block, so we don't need the previous hash right now, but after that we will need it. Now we print the hash values, print hashes, and we run our program to see the result. Yes, it exactly done what we expected from it. So we have now the hash value here 33, started with 33. Previous hash has no value, but the hash value has the SHA-256 of the data over here that we passed. We take the block takes these data and calculate the hash for the data, and the result is this hash function, this hash value. Then after that we define a block, so we need to define a blockchain. So we define another class is called blockchain, and also the blockchain has a constructor. Then the constructor of the blockchain, is also initial. It is standard in Python, so we don't change it, and it takes no parameter, and we define a chain in the blockchain, and this chain is a list of objects. The objects are blocks, so we define a chain of blocks. We put empty block, but we need to define the first block of the chain. To define the first block of the chain, we have to define another function is called generateGenesisBlock. This is the very first block of our tiny block chain. We pass self to it, we pass no parameter, and we return new block of values. We define 0 for the nonce, and with timestamp we put the first 2017, and the final data we just put something that define it is empty block, because it is Genesis block, has no values over here. That's it, we defined it. So we put the first block here by calling the generate self dot generate Genesis block, and we add a comma. So we define a list of blocks. Now we generate the startup block, which is called the Genesis block, and we now need to define some functions that is going to help us in defining the chain or adding block or something like that. So we define get last block of the chain. Get last block is easy to implement. We just return the last block of the chain, which is self.chain of -1. And if you know Python very well, you know that -1 refers to the last object of the list. So we defined the function that will return the last block, and then we add block. We need to define a function to add another block. To add new blocks, we pass the new block to the function. That's the new blocks that is going to be added. To add a new block, we have to define its previous hash value. The new block previous hash value is equal to previous hash value must be the previous block hash. It points to the previous block's hash. So the previous block hash is the last block. The last block dot hash. So the previous the current block previous hash refers to the previous block's hash, and the new block's hash must be calculated. So we have to call the calculateHash function. So now we have defined the previous hash, and then we define the current hash. We define the current hash, then the next block will point, his previous hash will point to the current hash, and so on. We have defined the new block, and we can now append it to the current chain by using the append method. So we pass the new block to it. Now we can add block. We can add block to the chain. We can get the last block. So we can build our chain right now. Right now we can build our chain. So we define chain, blockchain, is called B chain, or this is the coin. We call it OSA coin equal blockchain. We defined an object. It's called, this is the coin itself. So we defined an object. The object, we can add some blocks to it. The chain, this is chain, we can add some blocks to it. we can add dot add block, and we pass a block with new values like timestamp 20 of 5th 2017 and the transaction with $100. Okay, and we can add another block here with value 2 and 21 next day, and this is only $20. Now we want to print the blockchain. We want to print and see the inside values of the blockchain. So we have to go there to the print hashes, and we change it to the internal string function. This, when we print the block, we print the object, it prints what we have written here. When we call the print and we print an object of this class, it executes this function. So we implement it like that. We define a string, and this string equal like that. We can print the entire data. Just we take some time to write the exact shape that we want to print. String of self.nonce. String of self.nonce. Okay, and then string plus equal tstamp plus string of self dot tstamp string plus equal transaction. We put some space here so we separate the value from the title, so we print the self.transaction. And then finally string plus equal previous hash, and we forgot to do some plus here, and here we string dot self dot previous hash. Okay, previous hash, and then last one is string plus equal hash value of the current block equal string of self dot hash. Now we have the entire string defined. We can return that string. That's it. We can print the values right now. We can print the internal values of each block. So here we have added 2 blocks to the chain. We iterate for B. We iterate on all the blocks in the blockchain. So we iterate dot chain. Okay, and then print B. Print B will call this function. Okay, let's try it. Syntax error here. Yes, we didn't pass the self, and then we didn't add column. And so coin.chain, we have a problem here also for bn. Okay, now it's currently very good. We have the values, but it is not arranged very well because we didn't add the /n separator, so we have to add it to every value here, so we'll be able to see the values very clear. Okay, and last one problem. Now we execute, run the program. Now it's okay. If you see, the first block here is the Genesis block, and its nonce value is 0, and the value that we defined here, the same as we defined here. Then the hash value is started with 82, and the next block, its nonce is 1, and it is defined by the date we passed it to here, and the transaction value is 20. The transaction value is 20. So this is the one here, I'm sorry, this one, number 1, and the transaction value is 100, this one, and the previous hash started with 82. Here it is started with 82 for the previous block. So the previous block hash is the previous block's hash is the current previous block hash. So this hash also will be the previous hash value of the next block, and so on. So we have 3 blocks here, and every hash value, every block is connected to the previous block, and this one is also connected to the previous block. They have a similar values here. This value is similar to this value, and this value is similar to this value. They are connected together, so we can now we can we know that the block is a blockchain. The blockchain has connected values, and we have an integrity that cannot, or a chain that cannot be broken. If the chain is broken, so we can define an attack is happening, and somebody is trying to break the link. For now, we have implemented the block and the blockchain, and we have added some blocks to the chain. What about if we want to check if the block is valid or not? We want to know if the block is valid or not. So we have to define another function is called isChainValid, and it takes no parameters, and we iterate on all the blocks from 1. We didn't start by Genesis block to the self.chain length of the self.chain, that it is going to give us the length of the list, and we take the previous block. The previous block will be the chain of I-1, and the current block is equal to self dot chain of I. Okay, so we have in hand the current block and the previous block. We check if the current block dot hash not equal to the current block dot calculate hash. This means that we have to recalculate the hash again to make sure that there is nothing changed in the data. Nothing has changed in the block. The block is integral. It means it has no change. It's not a change. No change in it. So we return false. We don't have any change in the block. The block integrity is there. So we check another time by checking the previous hash value is not equal. If it is not equal, the current the previous block's hash, so we have a problem. If these two values are not equal, so we have a problem. We have to return false. Otherwise, if we didn't find anything, we didn't have a problem in the current block, we didn't have a problem in the link between the blocks, we can print a message here. So we define which condition is not met. So we print like invalid block before returning the value, and here we print invalid chain. Otherwise we return true. Okay, this is the function that we check the integrity of the chain and the integrity of each block. Now we will check if the blockchain is our blockchain that we have created here is integral or not, has integrity or not, perturbed or not perturbed. We have to define if it is perturbed or not. So we after the print, we can print the coin dot is chain coin dot is chain valid. Okay, we can run our program to see if it is true or not. Calc hash in line 37, current block, calc hash, maybe the spelling or something. Yes, spelling, calc hash. We can run it again and to define if it is working or not. Yes, it is true. It means that it is consistent and it has no change. So we have a valid blockchain and a valid block. Okay, now we test our integrity by supposing that there is a hacker and the hacker want to change the block. So the hacker may be here doing something like that. Chain of 1 dot transaction. He changed the transaction value to something like that. So the block now, block number 1, the block now which has a value of 100 is changed to 333. So the hacker has changed it, but we use the isChangeValid function to check if somebody has changed this block or not. So if we run our program again, yes, it calls an invalid block, and it says invalid block. We have an invalid block over here because the value is not consistent, and the value, if we calculate the hash will be different, because 100, the hash with 100 is different from the hash with 333. But if the hacker is smart enough that he can recalculate the hash like that, dot hash equal the same block, the same but here dot calc hash. So he recalculated the hash after it changed it, but now he has changed the value, and it changed the hash value too. So the block is good, the block has no change, but the link between blocks will be changed. So we expect to have another message here. Yes, it's false but invalid chain. It is invalid chain, not invalid block. The block is good, but the chain is broken. So we have defined a block, and we have defined a blockchain, which is the coin itself, and for now we understand how to make the blockchain and how to check the integrity and how to use the hash function inside the blockchain. For now we have defined the basic blocks of the blockchain. And thank you, and waiting for the next video that we will check the proof of work. We define how to make coins, and thank you for